Page 21, exponential regressions. So just to maybe give you a little overview of the unit. Yes, sure. I'll take this away later. But when you have exponentials, okay, you will be given, most of the time, the equation is just provided, right? You use that, you answer a bunch of questions. You can graph, you can do whatever you want with it, right? The next point will be where you are given a table. It's either horizontal or it's vertical. You know that this is x, this is y, or this is x, that is y. But we take this and we perform a regression, we come up with our equation, okay? So this one, I will spend maybe tomorrow a little bit of time on, but if you're given a table, I mean, come on, just L1, L2, perform your regression, come up with the equation, and then I can ask you a whole bunch of stuff. I can ask you to graph it, I can ask you for missing points, I can ask you for all of that, okay? What we're gonna do now is you have to create points. Okay? You have to create your own points, then perform a regression, then you have your equation. Okay? So instead of spending too much time on this, I will rather spend the time on creating our points, which is technically making a table, right? And then we perform the regression, we come up with our equation. So I'm going to spend a little bit more time here, and this I'm kind of just going to throw it at you as you work through it, and I would just expect you to basically use the skills you've learned here and apply it to this scenario, which I would argue is easier because I already gave you the points. You just have to type it in. Right? Something very important about exponential, folks, you need to have this somewhere on your study sheet, is doubling time and half-life. Okay, doubling time is how long does it take for something to double. It's an increasing situation. Half-life is a decreasing situation, right, where everything gets down to half as we go along. Okay, so put this aside. Let's do the question on page 21 here and see how this goes. Okay, and just a note, the next test, chapter 7, which is exponential logarithmic, you can also expect polynomials in there. Okay, so we're not going to forget about them. We're going to continue. It's kind of just going to build up. Obviously, it's going to be a bit more focused on exponential logarithmic, but don't forget about your polynomials, okay? So you still need to know all of that. Keep it on your study sheet. Okay, so we're going to do one with doubling time. Okay, the title kind of gives it away. So we're going to model, right? We're model regression. We're going to do one with doubling time. You should immediately know that this scenario will do this. Okay? We know doubling time, something is doubling. Obviously, you're increasing. I hope you know that. Which means B has to be greater than 1. Okay? So let's see what we've got here. A certain strain of bacteria is being observed in a petri dish and is known to have a doubling time. There it is. Doubling time of 7.5 hours. The initial population of bacteria is 2,550. Determine the equation that would model this scenario. Okay, I think we would all have to agree that our equation is going to look like this. Like the start will look like that, right? We already know that this A part, like let me back up because it's been a weekend. I know. Back up, just back up, right? This is what we're always aiming for if it's exponential. Another thing I have to say, I should have started with that, is that doubling time and half-life, you're thinking exponential functions, okay? You're not thinking, is this maybe a quadratic? Is this maybe a cubic? Like it's an exponential situation, right? So keep that in mind. We just don't know what B is. Like that's what we're trying to figure out. We don't know what this is. Question mark, okay? It has to be greater than 1, but we don't know. Because they don't tell us what percentage we're going up by a year, okay? We're not told that, okay? Or by the hour. So this is what we do. Create points. Using doubling time. And some of you will have a flashback to finance. How so? Yeah. No. Today's day 6. See you later. So this would be time, and this is population. Okay, so we're gonna say, this is crucial here. In this case, they don't give us a certain year, right? They don't tell us in the year 2000 you've got 2,550 bacteria. They don't tell us that, or right at 5 o'clock p.m. They don't tell us that. So we're just gonna start with 0 times 0. We've got 2,550, and you need to now provide at least 3 points. So what happens to your time? Like, what is the doubling time? It is 7.5 hours, right? So we're going to add 7.5 to 0, which gets us to 7.5. So doubling time means that what happens to our population gets doubled, right? So that's 3,100. Okay. 3,100. No. I was thinking 1,550. This is not right. What are we at? 2,500 times 2 is 5,000, and the 250s is 5,100. My bad. My bad. Okay. Do this one more time. Another doubling time happens, which means 7.5 hours have gone by. You're at 15. The doubling happens on the right side of your table, not on the left side. So this is 10,200. Here you have your table. We're going to make this L1, L2. We're going to go stat, calc, and what regression are we doing? We're doing exponential regression. Again, most of the time, the province will give you anyways, they will tell you what regression to perform. So let's try this. Stat, edit. Most common mistake I see, students seem to, they double both sides. They'll double this. First of all, what's 2 times 0? 0. So are you doubling? No. You're adding on this side. You're adding whatever the doubling time was. Okay? If it's 21 minutes, you'd add 21 minutes every time. Okay? So just be careful there. If you want to see the plot, I'm going to go to y equals. I'm going to turn plot 1 on, and I'm going to do zoom stat, right? So if you want to see them, it kind of looks like an exponential. The more points you feed this, the more it would look like an exponential. Okay? Let me try this here for you. I'm going to do stat edit. I'm going to do this one more time. What's 15 plus 7.5? 22.5? And what's double 10,200? 20,400? If I did a zoom stat now, including that extra point, now you see a bit more of a curve. We don't need that, okay guys? This fourth, I just introduced it. But the more you would introduce, the more this would look like an exponential function, which explodes at one point, right? It kind of has like, if we were to go to the negatives, it would be flat, and then all of a sudden it would explode up, right, at some point. So let's do the regression. Stat, calculate, and here you have to be careful, okay? Exponential, you gotta keep going down until you get to exponential regression, okay? It's option number 0. And then you do the same thing as before. Second 1, comma, second 2, comma, alpha trace, enter, and there it is. A doesn't surprise us because we knew that that was the initial. This is what we were after, okay? So I'll write that down. Y is equal to, do you get the same as me? Because I used 4 points. But do you get the same? Yeah, okay. It shouldn't matter. 1.0968. I'm just gonna do that because I feel like it. If you did 2 decimals, what would this round to? 1.10, 10, because the 6 bumps this to a 10, which bumps this to a 1. But so make sure you go 10 if you round to 2 decimals. Okay, so more, because it's not money, more is actually acceptable. So there you go. I didn't talk about, I want to talk about it because it's not asking for it. But what is this telling us? What's the percentage of increase every hour? This tells us that. Sorry. 1.0968 minus 1, you're left with 0.968. Oh, I'm missing a 0. Okay. I wish the bank would do that every once in a while. Just forget a 0 in front, but add a 0 at the back. If you multiply that by 100, you get 9.6868% increase per, what is my time here? It's not years, right? It's hours. So per hour, like that's what you found at the same time. Like as soon as you see this, you can use that to tell you what the increase is per hour. Okay, so that's also just an aside there. Next, what is the population after 36 hours? Hours is what we're in, so they're basically saying if my time is 36, what is the population of bacteria? So we're going to go second trace value, x is equal to 36, and you may have to adjust your window. Okay, I'm telling you already, you probably will have to adjust your window. Sometimes you get away without changing it. I will try it. Second trace 1, x is equal to 36. It gives me an error. I cannot do it. So it's most likely my window. Okay, so I'm going to change my x max to 50, let's say. And my y min is overkill. I don't need to go negative 400. The zoom function did that. I'm just going to go negative 10. And I'm going to bring this up to 40,000 maybe. Just expand here and here. Let's try this again. Second trace value, 36. It's 71,000. Okay, 71,000, 36, and 93. Can you state it like this? Is this okay in this scenario with the data that we're dealing with? What are we talking about? Population, right? This implies you need to round to a whole number, okay? This is not dollars, this isn't time. So you need to say approximately. I would just round it to this, okay? This would be the acceptable answer in this case. Bacteria, okay? Doesn't hurt to put down the units. Next, how long will it take for the bacteria to reach 14,500? how long, right? That's asking for time. This is 14,500. So if you know our y value, we will let y2 be that value. Okay, and then we're going to go second, trace, intersect, and let's find it. Most likely, I will just show you here, just a sketch, right? 14,500 is going to be here somewhere. And so we're trying to figure out how long it will take, right? There it is, second trace 5, enter, enter, enter. 18.81. And as long as you add hours to it, you're good to go. Decimals are fine here. Because time, it's continuous, right? Time is continuous. State one limitation of the equation in A. Let me translate this for you. When you have a question like this, they're kind of asking you to think long term, and they want you to basically say, like, why is it important to state a domain and range? Because it's not realistic in the long run. There's a problem, right? In real life, there's a problem. So what is a problem with the graph as you see it? Like if you look at the graph, if you start graphing here, if you do this, if you say arrowhead, what is that implying? Population grows indefinitely. It just keeps growing, right? Is that a problem? Even on this planet, it's a problem, right? If population just keeps growing indefinitely, we're going to be in trouble, right? So in a petri dish, right, bacteria can only grow so much, and then they're going to run out of food. They're going to overcrowd. They're going to starve off, right? It's just not going to work out. That's what they're asking here, and they do ask for real life. You to kind of envision this. They will give you enough information, but you have to envision this, right? You have to kind of think about what is the implication of this problem. So one would be population cannot grow indefinitely. Okay. Bacteria will run out of food, energy sources, and stop growing eventually. I asked you something like this in the on the test, like the cubic function, like what's the problem with screen time in the long run? At some point the screen time goes negative, right? How do you have negative screen time? Right? Like if you just keep going, it just drops. Some of you were saying, well, based on the pattern, like it shouldn't be going down, it should be going up, if anything, right? So yeah, just try to think logically and just answer accordingly, okay? Next, if the maximum capacity of the Petri dish is 95,000 bacteria, state the domain and range. So I'm capping it off. I'm getting rid of the arrowhead. That's what this is doing. I love my sketches for domain and range. So I'll say it grows, but then it stops, right? So we know that it stops here. It stops at 95,000. We started at 2,550. So this is my range here. This is what I have to deal with there. In terms of domain, I start at 0 times 0, and I will stop whenever I reach that 95,000. We need to figure that out. Can you see that, or? Sorry, guys. Especially if you're back there. move it up. This is my domain. So I have everything I need for the range, but I have to do a bit of digging to figure out what is the time here, like how much time has gone by to get to the 95,000. So we'll figure that out. Let's figure out the time there. So because we do know the Y, I have to change my window because my Y max right now is 40,000. So I'm going to go to 100,000 for my Y max. And you know what? As a good measure, I should probably increase my X max as well. I'm going to go to 100 there. Oh, I didn't make this 95,000 yet. So there, I need to find that X value, right, to tell me where time stops. So second trace 5. Just hit enter 3 times. You only have 2 curves. No big deal. 39.15 is my rounded answer. Okay. I looked at one of my students, actually in grade 11, applied. They had this on their study sheet, and I thought, you know what, this is actually great advice. So I'll put it up on the screen here. Domain is always left to right. You start left, you go right, like in that order. Range always bottom, then up, right? Like from the bottom and then the highest, the upper limit. So if that helps you, I'm going to leave it there for a bit. So for my domain, I go from left to right. So it'll be 0 to 39.15. Time stops, right? At 95,000, time stops. For range, I go bottom first, so 2550, all the way to 95,000. Boom, you've got it. I would argue that now you have everything you need to make a graph as well. I would just maybe say use your doubling timetable to help you out in between. Or, you know, if this is 0 and this is 40-ish, find a point like in the 20 range and maybe one more here just to help you out at the beginning, and then connect to that 95,000 there. And you're good to go, you're in business. Keep in mind that your range, right, you should be able to fit up to 100,000 on your Y, and for sure up to 40 on your x-axis. Okay. So that is that. We're good? Right. He went thumbs up. Thumbs up. Okay, let's go to 23. I'm going to do a half-life question.